Right, so the other topic I'm going to say something about is some methods of determining reaction orders, order of reaction with respect to reactants, and how to determine rate constants, right? All right, first, concept of half-life. Half-life is defined as the time it takes for a reaction to proceed to a point where the concentration of the initial concentration of a reactant as it is being consumed in the process has dropped to half that initial value. It's an indication of how fast the reaction goes, because obviously the shorter the half-life, the faster the reaction, right? Now, let's explore that concept for the simplest case, namely a first-order reaction. In the previous lecture, we saw that we can integrate the rate equation for a first-order reaction to produce the rate law in integrated form, yeah? And also in a linearized form, where we where we follow the variation of not A itself as a function of time, the concentration of A, but its logarithm. That turns out to be a linear dependence, right? Now, by definition, if we start with concentration A at time 0, we call that A naught. After one half-life, after a time has elapsed equal to T1 half, the concentration of A has dropped to half the initial value. So the A, concentration of A at time T1 half, is by definition A at the start divided by 2. Now, if we plug that into the general expression, the general solution of the rate equation, we get the following. So the A at T1 half, the A is equal to A naught upon 2. We plug that in for AT. This is a constant, ln A naught, so that stays there. And the T is equal to T1 half in this case. We get this equation, which is an equation in terms of T1 half. But let's first tidy up this expression, because it can be simplified. First of all, we transpose the ln A naught, carry it over to the left, and then combine the two logarithms in the usual manner. So a logarithm, one logarithm of one quantity minus that of the other, is the logarithm of the ratio of the two. So in this case, A naught upon 2 divided by A naught. That is what appears under a single logarithm, where you see that the A naught cancels, right? So we are left with the ln of 1 half being equal to negative rate constant times half-life. Now the ln of 1 half, again splitting the logarithm, is the ln of 1 minus the ln of 2. ln of 1 is 0, right? So we end up with minus ln 2 being equal to minus k times T1 half, or ln 2 equals k times T1 half. Then you divide both sides of the equation by the rate constant, and you end up with this relation between half-life and rate constant, which is a one-to-one correspondence between the two. Once you know T1 half, you can calculate K, and vice versa. Yeah? Now the ln of 2, of course, is a number. So if you punch that in on your calculator, you get 0.693 and a string of other decimals. Right? So this is so you see that in the case of a first order reaction, half-life is a meaningful concept. Yeah? It contains the same information as the rate constant K. Now to express this in graphical terms, let us now plot the graph of A as function of time. So we take the the anti-log of the linear expression that we saw previously, and you get a concentration of A at time t being described in terms of the initial concentration and the decaying exponential function, x minus kt, which looks like this. It tapers off to 0 eventually, right? So T1/2 in terms of this diagram would be the time taken for the concentration to drop from the initial A0 to half A0, which takes you here. So you mark off that point on the graph and drop a vertical onto the time axis, and that gives you the T1/2. Now, what is peculiar about first order reactions is that the T1/2 is independent of the starting concentration, because you don't see A0 in this formula, right? So if we now start off with A0 upon 2 and then ask the same question again, how long would it take for the concentration to drop to half of half A0, that is a quarter of this initial concentration, then you will find that it will take the same amount of time, T1/2, again. Yeah? And so on. And going from A0 upon 4 to A0 upon 8, again takes a time T1/2. Yeah, so that is why T1/2 is a very useful concept when dealing with first order processes. For example, radioactive decay. That the rate of decay is normally given in terms of half-lives for that reason. All right, now let's move on to the second order reactions. And the only one that we have analyzed in detail was that for the homomolecular process. So two A molecules coming together to form product. Now the time course of that process, as given in terms of the concentration of A at time t, can be cast in this particular form, again a linear form, where 1 upon the concentration of A at time t depends linearly upon time. It is 1 upon the initial concentration plus twice the rate constant times time. Right? Now again, we apply the definition of half-life this time to this process. So again, at time 0, concentration of A is A0, it's A0. After one half-life, that concentration has gone down to half A0. Right? Now to find out what the T1/2 in this case is, we substitute this defining relationship. So we plug in for AT the A at T1/2, so that is A0 upon 2 equals 1 upon A0 plus 2K times the T1/2. Now that is now the equation for T1/2, which and the T1/2 is then made the subject. First of all, we invert the thing on the left. 1 upon A0 over 2 is 2 upon A0. So that is 1 upon A0 plus 2K T1/2. Then we transpose this term. Yeah, so it's 2 over A0 minus 1 over A0 is 1 over A0. That equals what remains here, 2K T1/2. Then you divide on both sides by 2K. Yeah, get rid of the 2K here, placing it there. So you get half-life for the second order reaction being equal to 1 upon 2 times the rate constant times the initial concentration of A, of the reactant A. So this time you see that T1/2 not only depends on the rate constant, but also on the starting concentration A0, right? So that makes T1/2 a less useful concept for the case of second order reactions. You can always define it, but you might always almost ask, why bother? Right? So if you look at that in terms of the graph, yeah, for A as function of t, which is also a decaying function. Yeah, of course, because A is constantly being used up in the process, so it is a decaying function, but not exponentially, right? Okay, so if we now start with initial concentration A naught and wait for a time t1/2 for it to fall to half A naught, then the time it subsequently takes to fall off to a quarter A naught, so half of half A naught here, that time will be longer, will be twice as long as the first t1/2. No? And that has to do with the fact that t1/2 is inversely proportional to the starting concentration. So if the starting concentration is less by a half, right? What that implies is that t1/2 for the subsequent reduction in concentration by 1/2 is twice the time it initially took to go from A naught to half A naught. So to go from half A naught to quarter A naught will take you twice as long. Yeah. And that half-life again doubles in the next in this interval, yeah, during which the concentration drops from quarter A naught to 1/8 of A naught, etc. So t1/2 then is less of an unambiguous concept than it was in the case of first order reactions. Right? So that is in short the notion of half-life. Now let's go back to the main task of kinetic experimentation, kinetic analysis. That is the determination of rate laws for a given reaction. Now, as I already pointed out a couple of times, the rate laws for any given reaction can only be determined experimentally because of vast theoretical problems, right? Mathematical problems. Now, what kind of techniques do we have at our disposal? Well, there are many. There's only 4 listed here. The very common technique is the measurement of absorption. In that case, you use a spectrophotometer. That is the instrument being used. And if you have a reactant that absorbs quite strongly in the preferably in the visible region of the spectrum, you then tune in to the wavelength at which the maximum absorption occurs. And you measure the absorbance of the reaction mixture at that frequency, which is an indication of the concentration of that reactant. It's actually directly proportional to that concentration. Yeah? And then as the reactant is being used up, you will see the peak height gradually decrease, and you can, well, draw your conclusions from that. Yeah? Another very useful technique, well, useful in the case of relatively slow reactions, is the technique of conductivity. And that is because many reactions of interest, inorganic reactions, take place in solution, aqueous solution typically, where the compounds tend to split up into ions, right? The ions, of course, if you apply a voltage or an electric field to the solution, will act as charge carriers and basically producing a current in response to an applied voltage. So by measuring the current relative to the applied voltage, you get a quantity known as the conductance. Conductance also depends on, well, the electrodes, the size and distance between the electrodes, but if you eliminate those geometrical effects, you end up with a property that is characteristic of the solution itself and its contents. So the ionic concentrations and the types of ions, because each ionic species is characterized by what we call an electric mobility. Yeah? So how fast does it move under application of an electric field. So conductivity basically is a measure of the ionic content and is also determined by the types of ions. Now, when a reaction occurs in the solution, of course, the composition of the solution changes. So you may have fast ions like hydroxide being replaced by slower ones like chloride ions, which will show up in a conductance measurement as a lowering, as a decrease in the conductance, right? So conductance measurements is a very suitable method to monitor reactions between ions in solution, provided they're slow enough so we can actually follow the process using a conductance meter. Another one that is listed here is polarimetry. Well, polarimetry is applicable if you study reactions between compounds that are optically active. That is, if you have them dissolved in solution, in water, say, and you shine polarized light through that solution, the plane of polarization of the light is turned, yeah, by the solution, and the degree to which that plane is turned is directly proportional to the concentration. So if you have for example, a mixture of alpha and beta glucose, yeah, different stereochemical forms of glucose, the one compound turns the plane of polarization in one direction and the other in the opposite direction, so that if you have an inversion taking place between the two, you will find that the plane of polarization will turn in the course of time. And by monitoring the rate at which that occurs, you can then say something about the rate of the process, the kinetics of the process. A fourth method that is listed here is called the aliquot method. Well, if there had been a lab this week, that is the one that you would have been practicing in the lab. This time you're only going to process some model data. I will say something more about that method later on, because it's topical, of course, with the kinetics experiment being on this week. Now, what method is based on is that you, if it is a very slow reaction, like that hydrolysis reaction of ethyl acetate, then what you do is at set intervals you take a sample and you titrate, say, an aliquot from your reaction vessel and quench it, basically stopping the reaction. Then you, if it is an ion that is being produced, or an acid or base, you can titrate it. You know? Don't be too slow, because the reaction is still going on, be it at a far lower rate. But it will give you an indication of where the reaction has reached at the time that you quenched your aliquot. Yeah, and you do that for a whole series of samples. Now, we will be mainly concerned with reaction mechanisms that lead to a rate law of this form. So the rate of the reaction, defined as the rate of difference of either A or B, or the rate of appearance of the product P, equals the rate constant, which is a function of temperature, times the concentration of A at the given instant, raised to the power m, the order of the reaction with respect to A, times B to the n. And the aim now is to find m and n, as well as the rate constant K. There are two general methods that are being employed here to go about this analysis in a systematic manner. The first one is known as the isolation method. suppose we have this binary reaction between A and B. But the trick then is to have one of the reactants, say B, present at a very high concentration in a large excess with respect to the other reactant A. What that means is that, say, if B is present at 1 mole per liter and A at 1 millimole per liter, even if A has been totally used up, then the concentration of B is still like 999 millimolar, right? Which, for all intents and purposes, is 1 molar. So the fact that A has been consumed fully has not made a significant dent in the concentration of B. By having B present in excess. That means that B, throughout action, the concentration of B is essentially constant. And you can actually combine it with the rate constant K. Yeah? So that the only variable here in this rate law is the concentration of A, which of course considerably facilitates the analysis. Right, so if you do that, you would write the rate law as, well, a pseudo rate constant, which is defined as K times that essentially constant concentration of B raised to the power n, times the varying concentration of A raised to the power m. Yeah, and this rate expression can be very easily analyzed. Well, it is a power law dependence, and the standard procedure is then to turn that into a linear expression by taking logarithms on both sides. So you take the log of r, that is the log of k primed, times this. You split the logarithm into a sum, so the log of k primed plus the log of a to the m, where the index m then comes in front of it. Right? So that has produced, therefore, an integrated or a rate expression, a rate law, in linear form. Yeah, y, the dependent variable, equals a constant plus the index m times the running variable, the independent variable log a. So if you determine r, the rate of the reaction, at a number of times where you know that the concentration of A is A at that time t, you plot log r versus log A, you should be getting a straight line with a gradient m, which is the quantity that we are interested in, right? Well, the intercept is also interesting because that contains information about k. Remember, k prime equals the k, the actual rate constant times the concentration of B, which is the initial concentration essentially to the n. But of course, we still don't know what n is, right? So that now to find n, what we do is we simply reverse the roles of A and B. So rather than having B in excess over A, we do have it the other way around. So now we add a large concentration of A, low concentration of B, and that will, using the similar procedure, will lead to the value of n, right? And then you work back and find, now that you know n, you can find also k, the rate constant, and you have all relevant information there, right? Okay, now this slide I have inserted because it's pertinent to this week's experiment that you're analyzing. It concerns the acid-catalyzed hydrolysis of ethyl acetate. Ethyl acetate here reacting with water. This is an example where you have one of the reactant indeed present in excess, namely water. Yeah? The concentration of water will not be affected to any significant degree when you have ethyl acetate reacting in it, right? Okay, request about the previous slide. Okay, so the idea of the isolation method is to, for a binary process, is that you have one of the reactants present in large excess with respect to the other, so that the concentration can be essentially regarded as constant. That means that you can simplify the rate law like this, where K primed is time independent, essentially. Right? So the only time dependence is in A. Take logs on both sides, you get this, a linear form. Measure, the thing is that at certain time intervals you measure R and A, right? And then you plot the log of R versus the log of A. You get a straight line with a gradient equal to the index or order with respect to A, right? That is the idea behind the isolation method, rather than you having A and B varying at the same time. Then you don't know what you're looking at. Okay, now look at this particular reaction, which is again of a pseudo first order type. Yeah, it's a second order reaction. Yeah, it involves one ethyl acetate and one water molecule, but because water is in excess over concentration of ethyl acetate, its concentration is essentially constant. Yeah. You need acid as well to make the reaction proceed, and that produces another acid, which is the acetic acid plus ethanol, right? Now the idea is to write the rate equation as the rate of loss of ethyl acetate. Yeah? So the decrease in concentration of ethyl acetate with a minus sign defines the rate, which equals the rate constant times the concentration of ethyl acetate at a given time times the concentration of H2O, which is a constant. So we absorb this concentration H2O into a single constant K primed together with the actual rate constant K. So this now has the form of a first order reaction, right? Even though it is strictly speaking second order, but because of the mathematical form, it is now what we call pseudo first order reaction. Well, we have the integrated form of that. Again, write it in linear form as the logarithm of concentration of E at time t equals the log of E at time 0 minus the pseudo first order rate constant K prime times the time. Now, what is the idea behind this aliquot method that you apply in this case, because it's a very slow process? Now, what you do is at set intervals, you take a 5 ml aliquot out of your reaction vessel, right? And you quench it. And you do that by running those 5 mils into ice water, a large volume. And the reason for that is twofold. First of all, because it's ice water, it's cold, which by itself will slow down the reaction. And also there is the effect of rapid dilution. That means that the ethyl acetate molecules and the protons that are necessary for the reaction find it hard. For them it is harder to find each other. That will also slow down the process. So basically the process comes to a halt by the quenching step. No? Then subsequently, what you do is titrate the solution with hydroxide, which mops up the protons that came in as catalyst, as well as the protons that are being stripped from the acid that is being produced, which is variable, that increases in time. Right? The titration gives you an idea of how far the reaction progressed at the point at which you reached your aliquot, the 5 mil aliquot. Do that a number of times. So, okay, the question here. Right, so you have ethyl acid and water plus some hydrochloric acid catalyst. As the reaction proceeds at room temperature, then form acetic and ethanol, right? So that's the conversion that takes place. So you have acid, right? Now there is an acid present all the time, that is the catalyst. If you stop the reaction by quenching an aliquot, make sure it's the same amount each, and you then titrate that mix, yeah, which contains two acids, HCl and the weak acid. You titrate it with sodium hydroxide. Yeah. Then, in the course of time, you will find that you need more and more sodium hydroxide to reach your endpoint, your titration endpoint, because more and more of the acetic acid is being generated, as time goes on. So you sample your reaction mixture at set times, and do using 5 mils each time, titrate with sodium hydroxide. Now, of course, when the reaction is complete, so all of this ethyl acetate has been converted into acetic acid, well, ethanol, then of course the titer volume will be at a maximum, because you have reached the maximum concentration of acetic acid. So at that point, we call that titer volume, we call that V infinity, right? It is a direct measure of the amount of acetic acid that has formed, and hence the amount of ethyl acetate that you started off with at the beginning of the experiment, right? So that is V infinity, so that is the final titer volume. At some intermediate point, time t, say the time of quenching after the start of the experiment, your titer volume V at time t, which has, well, the same quantity of HCl in it. So that has to be titrated first. And also the weak acid is present, but not to its maximum degree, right? So Vt is less than V infinity. Now, if you take the difference between the two titration or titer volumes, you cancel out, first of all, the constant volume that is needed to titrate the hydrochloric acid, which is the same in each titration experiment. And the difference that you're looking at is really the difference in acetic acid, at its maximum, that means at the completion of the reaction, minus that at some intermediate stage. Now that difference, of course, is a measure of the ethyl acetate that remained at time t, because V infinity minus Vt measures the is a measure of the quantity that has been converted, right? So V infinity you can consider a measure of the initial concentration of ethyl acetate. That is the maximum value. At time t, it is a measure of the amount of ethyl acetate that has been converted up to that point. That means the difference between the two measures the amount of ethyl acetate remaining at time t. So the instantaneous concentration of E at time t is measured in terms of a difference in the titer volumes, the aliquot titer volumes at infinity and at the current time t. And the constant connected to is independent of t. It's just a real constant, right? making sure that you keep the same 5 ml aliquot volume each time, of course. Yeah, if you plug that proportionality into the integrated rate law, that constant will cancel out on both sides, and you're left with the ln of v infinity minus vt here equals ln of v infinity minus v at 0, which is, well, the v at 0 should be the titer volume corresponding to pure hydrochloric acid, minus that rate constant times t, right? So again, the degree to which ethyl acetate has been converted is measured in terms of the titer volume, where you titrate the acetic acid that has formed, right? And that titer volume increases over time as you get more and more of the acid. Yeah, and remember, these are just samples that you are considering. Yeah, 5 ml samples of which gives you a snapshot of the reaction mixture at that point. Yeah, the titer volume tells you how much acid has formed, right? Or conversely, how much ethyl acetate has been lost, right? So that is what the V at T measures. Yeah. Now V at infinity, there you have lost all the ethyl acetate that you started off with. So V infinity is a direct measure of the initial concentration of this ethyl acetate. Yeah. VT tells you, right? Okay, you want to ask something, Nadisha?
Okay, sir. So from what I'm understanding is that throughout the reaction, basically at different time intervals, you take a sample of the mixture
Yeah.
that would contain different concentrations of acetic acid as the reaction progresses, and then
Yeah.
you titrate it with sodium
Hydroxide.
hydroxide in the concentration of the acetic acid.
Right. Yeah. Of course, you always have to use the same volume to get rid of the H plus catalyst, from hydrochloric acid. But then there is the added tighter volume that corresponds to the acetic acid, right? And that is the one that is varying over time. If you make up this difference in tighter volumes, this constant contribution will always cancel out. Yeah? Because the aliquot that you pipette from the reaction beaker is always 5 mils, right? Yeah. So we are now concentrating on how much acetic acid forms after a time t, and that is measured by Vt, right? So it is at the maximum at the end of the reaction when the conversion of ethyl acetate is complete, right? So this is always the largest value, V infinity. And Vt measures how much of the ethyl acetate has been converted into acid, right? So that V infinity minus Vt is a direct measure of what remains as ethyl acetate at time t. You get me?
Yes, sir.
Okay, and then you plug in this proportionality relation in the integrated rate law, cancel the common factor, the proportionality constant, and you get the ln of V infinity minus V at time t equals this constant ln E naught, which is ln V infinity minus V at time 0, minus K prime t. All right? So the idea then is to plot ln of V infinity minus Vt against t. And that should give you a straight line with a gradient equal to a negative gradient equal to minus the pseudo first order rate constant, which is K times concentration of water. Yeah, that is the aim of that experiment. And if you look at your worksheet, then you will see that well, you will have an idea of why that is being done that way, right? Good. All right, so the isolation method, that is where we were. Well, that's, I already told you to find the index or order with respect to the second compound B, reverse the roles of A and B. Yeah, and that gives you the second index N. And once you have M and N, you can then go back and find K, the true rate constant. All right, next method, second one, is called the initial rate method. In that method, again, you perform a series of repeat experiments where you systematically vary the concentration of one or the other reactant. So it is the initial rate that you measure. So within the first, well, few seconds or hour, depending on how fast the reaction is. So you determine the initial rate and then perform another experimental run, but varying the concentration of one of the reagents, right? Okay. Now, how does that work? So suppose we have a reaction again of this type, a bimolecular process. The initial rate, the rate at time 0, is the rate constant times the initial concentration of A raised to its index A, which is the unknown, times the initial concentration of B raised to the order B, which is the other unknown. Again, because of the power law dependence, we take logarithms on both sides to turn the indices into factors. So we get the log of the initial rate equals the log of the rate constant plus index with respect to A, order with respect to A, times the log of A at time 0 plus B times the log of concentration of B at time 0. Now suppose that we perform a series of experiments in which we start with the same concentration of A, but we vary the concentration of B from one run to the next. So the log of B naught then becomes the variable, the independent variable. Whereas the first two terms for this type of experiment combine into a single constant, C. Yeah? And the left-hand side is then the dependent variable. So if you then measure that initial rate by systematically varying the concentration of B at constant concentration of A, and then plot the log of initial rate versus the log of the concentration, the log of concentration of B, the initial concentration, again, you should get a straight line with a gradient equal to this factor here, B, which is the index with respect to, or the order of the reaction with respect to B, which is one of the unknowns. And the intercept we're not interested in for now. The next series of experiments, which are aimed at finding the other index, A, we then do the same thing. So we have a series of initial rate measurements where we keep B naught constant, the initial concentration of B constant, and we vary the concentration of A. And then perform the same analysis, and that will yield the index A. Then the next thing to find the rate constant, well, what you could do is just take any of the results of any of those experiments with a particular value of the rate naught, initial concentrations A naught and B naught. The A and the B are now known, so you plug those in as well, which leaves only K as the unknown, which you then calculate. Right? Now there are also simpler methods than that, where it only suffices to have 2 or 3 kinetic runs done to find the indices A and B, rate constant K. An example is given here, and there's another example which you will find on the first tutorial or second tutorial paper. So that is not on for next week yet, but the week after. Right, so suppose we perform one initial experiment, yeah, with concentration A and B. The unknown orders A and B are there, and the rate constant K. And you measure the initial rate R1 under the conditions that concentration of A is this and the concentration of B is that. Now, a second experiment is then performed, which you keep the concentration of B fixed, and you change the concentration of A by a factor. Say you double it. Yeah? So you multiply the concentration of A by a factor n, or if you dilute it by 2, then it's n equals 1/2, right? So n is a known factor. And then you determine the initial rate again, find a different value in general. Now you compare those two results. And you do that by dividing the second by the first equation, because a lot of common factors you will find canceling. No? If you do that, you get R2 equals K times, well, the NA to the A times conc B to the B divided by the initial rate constant with concentrations in B. Now you see the K cancels from that resulting expression, as well as the factor B to the B, yeah, leaving N to the A times A to the A over A to the A, and then the A to the A cancels as well. So we get the either concentration or dilution factor N raised to the power A. And A is the unknown, so that should be made the subject. And remember, R1 and R2 are the results of measurements, so you know what they are. Right? Now, A being an index, to find it, you, of course, take the log of this formula. So the log of R2 upon R1 equals the log of N to the A. And then you bring the A in front of the log and divide through by the log of N. And that gives you the value of A. Yep. And A should be either an integer or a half integer. If it's not, then you will have to round off to the nearest integer or half integral value, right? So for example, if you find that if you double the concentration of A, so N equals 2, and you find that the initial rate doubles as well, yeah, so you get R2 being 2 times R1, you cancel R1, so you get a log of 2 divided by the log of N equals 2, so which is 1, of course. So that means that your reaction must be first order with respect to reactant A. If, on the other hand, upon doubling the concentration of A, so N equals 2 again, you find that the initial rate quadruples, so R2 equals 4 times R1. To find the order with respect to A, you then use this formula. So you substitute for R2 4 times R1. So 4 R1 upon R1 is 4. With the log of 4 divided by the log of 2. And 4 is 2 square. So you bring the square in front. So you get 2 times log 2 upon log 2 is 2. right? So in this case, the order of the reaction with respect to compound A is 2. It's a second order reaction with respect to A. Right, so if the rate doubles, we saw it must be first order. If you double the concentration of A, if it quadruples, it is second order. And if it increases by a factor of 8, it is third order, etc. Right? To find the order with respect to the other compound, B, of course, you perform a similar couple of experiments, but with the roles of A and B reversed. So this time you keep A constant, and you say you double B, going from this to that. Yeah? And that gives you lowercase b, the second order. Once you have A and B, then you take, say, the first equation, R1 equals K, A to the A times B to the B, with the A and B concentrations that prevailed in that case, and the known A and B substituted, and then find K from there. Yeah, and you're done. Right? So that brings this lecture to a conclusion.